let's see what are the time and space complexities of decision trees. Let's try to understand the time and space complexities in both the training and also in inferencing. Okay. First, let's try to look into training. So here, let's consider the training data set with n samples and d features. That is, in this data set, we have n number of records and d number of features. Okay. So now let's try to understand how much time it is going to take to build a decision tree using this training data set of n samples and d features. And as we know, each of these features can either be continuous or can be categorical. Okay. And in one of the videos, we have seen that if the cardinality increases for the categorical variable, then the partitioning method won't work. That is, if you remember, for any categorical variable with k distinct values, there can be total of 2 power k minus 1 partitions are possible. But if we try to compute the impurity for all of these combinations, it will become very complex if this k increases. That is, if the number of distinct values increases. That's why in one of the other videos, we have seen how can we convert a categorical feature into the numerical feature using one of the techniques called supervised ratio method, which is also known as the target encoding. So in this scenario, let's assume that we have all the features as continuous, all these D features as continuous. That is, assume that even though we have some of the categorical features, let's say we converted them into numerical. Okay. So assume that after all the pre-processing, we have D features where every feature is continuous feature. Okay. So now let's just recall the process. So whenever we have a continuous feature, what do? The first step, we sort the values, right? We sort the values in the continuous feature, and then we compute the impurity for every split, that is for every unique value. Okay. So the first step is to sort the values in the continuous features. So the worst case time complexity for sorting the integer values is nlogn. Okay. So nlogn is the worst case time complexity to sort the list with n samples. Okay. So, but we need to sort all the features, right? To sort one feature, it takes nlogn time. So to sort D features, it will take D into nlogn time, right? So now let's see. So we know that to sort one feature, it will take us nlogn, but to sort D features, it will take D into nlogn. So I'll write the time complexity here. I'm writing big O of. So we have nlogn time to sort any feature with n samples, but we are going to do it for all the D features. So I'm multiplying nlogn with D. So this is the time complexity. So what do we do after this? So once we sort all the values in all the features, then for every possible split, we try to compute the impurity and choose the better threshold, right? So how much time that is going to take? So once we sort the list with n values, what do? For each of the values among these n values, we compute the impurity and take the one with the less impurity. So that requires us to parse all these n values, all these n sorted values. Okay. So that's order of n. And again, we need to do the same thing for all the features. Okay. So it's not only for a single feature, we need to compute the impurity for all the features for all the unique values, right? So it will add an additional time of, order of n to parse the sorted list or the sorted feature into D, because we need to parse all the features, all the values in all the features. Okay. But asymptotically, we don't need to make this kind of big notation, because among these two terms, this is the dominating term. Okay. This is the dominating term. So we can just represent that alone. Okay. So asymptotically, this will be equivalent to order of n log n into D to compute each node. Okay. So this will be the worst case training time complexity in decision trees. Okay. Order of nlogn into D. Okay. So this is the worst case asymptotic time complexity of decision trees. Okay. Now let's try to think the space. And whenever we think the space asymptotically, we always look for the extra space. Okay. Extra space. So what do I mean by the extra space? We should never include the space that we took for the inputs, because we already have the data set with the size n cross t. It's like an n cross t matrix, but this is the input. We shouldn't consider the space that we took for the input. We should see how much extra space does the algorithm is taking other than input. Okay. So other than this input matrix, what else do we need? So other than this input matrix, we just need the space to store the tree. Okay. We construct the tree from this data set, right? From this training data set. So this is the tree that we construct. So how much space do we need to store this tree? So what does the tree contains? The tree contains nodes. And what does the nodes contain? So each node contain each condition, right? So each node will have some if-else condition. So the decision tree model is nothing but a bunch of if-else rules. So we just need to store all those if-else conditions. So that will be equivalent to the number of nodes, right? Because every node will have a condition, will have a if-else rule. So the space we take to store the tree or to store the if-else conditions will be equivalent to big O of nodes. If you have 500 nodes in your decision trees, then you need to store 500 conditions, right? So that will be equivalent to big O of nodes. So these are the time and space complexities for training. Okay. Now let's say we completed the training process. Okay. We completed the training process. So after completing the training process, what do we get? We get a decision tree that we have constructed using this training data set. Okay. So now using the constructed decision tree at the time of training, now we need to make inferences. It is also known as testing or scoring. Okay. So let's say we got the new query point, which I'm representing with X subscript Q. It's a new query point that we got. Okay. And it's a d-dimensional vector. Okay. It's a d-dimensional vector that we got. So now using the decision tree that we have constructed at the time of training, we need to make prediction for this new query point xq. And how do we do that? It's very simple. You already have the tree that you have constructed. We just need to parse this tree from top to bottom, right? We just need to parse this tree from top to bottom. In worst case, you know how much time it's going to take to parse the tree. In worst case, we might start from the root node and we might end up with the very leaf node, like the leaf node at the maximum depth. So in worst case, at the time of inferencing, we might need to parse the decision tree from root node to leaf node at a maximum depth. So that will require us to parse the tree at the very maximum depth. So the time complexity, the worst case time complexity will be big O of depth. Okay. So this is the time complexity for inferencing. This is actually very less. That's why we use decision trees for low latency applications in like more internet applications. When we want the predictions like very quick, we can go with the decision trees. But because it's very simple, we just need to parse the tree from top to bottom, right? And what is the space? Again, all you need in the memory is only the decision tree. That is those if-else conditions, those if-else rules. So again, here also the space will be equivalent to big O of nodes. Okay. So these are the time and space complexities for both training and also for the inferencing. Thank you.